Let's take a look at object-oriented programming in Roblox Studio. Now, Lua is not an object-oriented language, it's a functional language, but we have the ability to imitate object-oriented programming by using tables and metatables. Now, object-oriented programming is a programming model based on the concept of objects. Objects can have their own unique properties that can be manipulated, and these objects are created by something called a class. You can think of a class as a blueprint, and this blueprint can create many different objects with different properties. For example, a blueprint for a car can tell you how to create a car, but then you can change the tires on your car, you can change the color, you can tint the windows, and so on. Not all cars have to be the same. An example of this would be any object ever in Roblox Studio. For example, this part here you can consider an object. It has its own unique properties that you can manipulate, such as the size or the color, the transparency of the part. And I can make multiple different parts, and all of these parts are separate from each other. They are all different objects that can have their properties manipulated. For example, I can make this one red, and I can make this one blue. They're two different objects, and then I can resize this one to a different shape. And there you go. You have your three separate different objects with different properties. That's the general idea of object-oriented programming. So we can use tables to represent objects because they're just going to be a container of properties. And then we can use metatables to store functions that can be used to manipulate those tables or our objects. If you don't know how to use metatables, I recommend for you to check out my video on metatables first. Link will be in the description. Now, I think the best way to demonstrate object-oriented programming is to replicate Roblox's own Vector2 data type. The Vector2 data type is basically a class. It has a .new function to create or construct new vectors, and this function is called a constructor because it creates and returns a new Vector2 data type. This constructor takes two inputs, an x and a y value, and it returns to us an object that is of the type Vector2. Now, commonly, Roblox developers will use module scripts to store all of the code for a particular class, and then other scripts can require that module script and construct objects with it. So let's create our own custom Vector2 class. I'll just make a new module script inside of server script service. I'm going to call this my Vect2, and this is going to be my Vector2 class. So I'll rename this to Vect2. This table right here is basically going to act as my class. And then I'm going to create another table. I'm going to call it MT, short for metatable. And the purpose of this table is to store all of the functions that we're going to be using to manipulate Vector2 objects. Because if you think about it, with Vector2 objects, there's a whole bunch of different functions in here you can use to manipulate them. You can pass another vector and get a scalar dot product. You can lerp Vector2s, you can get the cross value. There's a bunch of different functions that you can do to manipulate these vector objects, and that's what our metatable is going to store. It's going to store those kinds of functions. So let's first start this off by creating a constructor. It's just a function, and typically it's given the key or identifier of new. So we'll create a new function inside of our Vector2 table, and we're going to call it new. And we need to take two arguments, one's an x value and one's a y value. There's our constructor. So now what we need to do with our constructor is we need to create a new table that's going to act as our object. So I'll create a new table in here. I'm just going to call it self, and I'm going to set it equal to an empty table. We're going to talk about self in a little bit, so don't worry about what that is for now. And then I need to make sure that I set the metatable on my self table with this metatable up here. Currently, there's nothing inside of it, so I'll show you what we need to do in a little bit. But afterwards, inside of our self table, we can store properties for our Vector2. For example, we can store the x coordinate. We'll set that equal to the x. And we need to store the y coordinate. We'll set that equal to the y. And then, very important, we need to return this newly created object back to where this function was called. So let me go and require this Vector2 class. And then what I'm going to do is I'm going to create a new vector object. And that's going to be equal to my Vector2. And we're going to do .new. And we're going to pass our value, which is, let's say, 1 and 2. And then let me make sure to actually return this Vector2 table at the end of my module script. Don't want to forget to do that. So now our constructor should actually autofill. There it is. So we need to give it an x, which is 1, and we'll give it a y, which is 2. And then just for fun, let's print this out into the console. So we'll print our vector object. Let's go ahead and run this code. And what you're going to see is we have a table with an x coordinate of 1 and a y coordinate of 2. Very cool. Now we can expand upon this. Wouldn't it be cool if with our vector object, we could call a function on it like dot and pass another vector object to get a dot product? So let's go ahead and take a look at how to do that. First, we need to define a new function that we can call upon our objects. And we're going to store this function within our metatable. So we'll call this our dot function. And we'll get past another vector2 object. And from this point is where we could return a dot product. Now, sometimes we might want to verify that this object being passed to this function is actually one of our vector2 objects that has an x and a y coordinate. Because what if somebody passes a string here, or an empty table, or whatever else in the game? So one way that developers put identifiers inside of their objects is they'll create another key, and they'll typically call it __ type. This is not an actual meta method that exists. It's just the name they decided to give for it to help, identify these different objects, and they just usually give it a string name like vector2. So that way, when this object gets passed to our function, we can check if it's a table, and if it's a table, we can check if it has this __ type key inside of it with this string of vector2. If it doesn't, then we need to, throw an error and say, hey, you passed the wrong value to our dot function. So typically what we'll do is we'll check if the type of the value passed here is not equal to a table, we need to throw an error. Or if it is a table, it does not have this __ type key inside of it, and that value is not equal to vector2. So this is how we can detect if the value passed here is not the correct value. So if it is, we can throw an error and say, incorrect value passed to dot function. Otherwise, it's really easy to calculate the dot product of two vector2s. All we need to do is multiply the two x coordinates together and the two y coordinates and add those values together. So that's what we need to return here. Now you might notice a problem. We have access to the second vector, but how do we refer to the original vector? Because we need both to calculate the dot product. Well, something I want to show you real quick is that if we created a new vector2 data type, right? And we were to call the dot function on it, and we were to pass another vector2 object, both this vector object here and this vector object here is going to be passed to our dot function. Now, the reason is because we're using a colon here instead of a dot. What's the difference between using a colon and a dot? Well, if you use a dot, it's simply going to execute this function, and the first argument passed to the function is going to be the one passed right here, and it's going to completely ignore this other object. But if we call it with a colon, the object that we are calling this function on, which would be this other vector2, is automatically passed to our dot function. So this, let me copy this, is the exact same thing as if we did something like this. This is actually a bad example. Let me go ahead and create a variable for it. I'll just call this my vect. So we'll do vector2.new, and then we'll refer to our vect, call the dot function, and we'll do something like that. And then let me copy this and paste this down here, and instead replace this with a colon, and then get rid of this. So this right here is the exact same thing as this. They both do the exact same thing. It's just our vector object is automatically passed to our dot function when we use a colon rather than a period. And this is where the self keyword comes into play. Because I have denoted that this function can be called with a colon, that means whatever object this function is called upon is going to be automatically passed to this function as a hidden parameter called self. That's what self is. Self refers to the object that was automatically passed to our dot function. So that means we can return, referring to our original object, which is self, get the x value in that, multiply it by the x value of our other vector, and then we can add the product of the y component multiplied by the y component of our other vector. So this is how you calculate a dot product with a vector2. If you wanted to create your own vector3 class for some reason, then you would also add one last section for the z coordinates. All right, very cool. So now what this means is we can create one vector object here, And then we can create another vector object. So we'll call this vector object 1. This is vector object 2. And we'll set this one equal to vec2.new. And we'll do like -1 and -1. So now if we refer to vector object 1 and we call dot, we should be able to pass our vector object 2. So let's go ahead and run the code. And what you're going to notice is that we got an error. Attempt to call missing method dot of table. Wait a second. I thought we already defined the dot function right here. Why isn't it working? Well, think about it. If we go back to our constructor, when we construct these new objects, our table only has an X and a Y coordinate inside of it, and this additional other key called type. This object, or this empty table, doesn't have any functions in it, so it doesn't know about this dot function. Now you might be thinking, but I thought we attached this metatable to it. Well, you gotta think what metatables do. Metatables store meta methods that get executed in specific circumstances. We have not defined any meta methods inside of our metatable. Therefore, when we tried to access our object with a key, in this case that is dot, that didn't exist, we ran into an error. Now we can fix this problem very easily by defining a meta method inside of our metatable called __index. And this meta method gets called or executed or used when we try to index a table with a value that does not exist. In this case, what I'm going to do is I'm going to define the __index meta method to be equal to the metatable itself. Now you might take a look at this and think, what the heck is going on? But if I run my code, you're going to see that we're still going to run into an error because the command line is kind of buggy with module scripts. So what I actually need to do is I need to run the game instead of using the command line. And let's go ahead and see. Oh, look at that. No error in the console. So let's go ahead and see and print out what is returned from our dot function. So if we run the game, there we go. We get a value of -3. That is our dot product. Now you might think, wait a second, I thought dot products only go from -1 to 1. And you'd be correct. The reason that we got the value of -3 is because we have not converted these vectors into a unit vector, or aka a vector with a length or a magnitude of 1. So let's actually define another function for doing that. Now before we actually create that function, let's go back to this little magical meta method right here. You might be wondering, why did our code work by just adding this line right here? Well, let's go into the mind of the Lua interpreter, right? When we create our new Vector2 object right here, we just got returned a table that has a value of 1 and 2 with this metatable attached to it. And then we created another vector object with a value of -1 and -1 with the metatable attached to it. Now what's going to happen is that when we call the dot function on our object, the interpreter is first going to check inside of our object directly if it has this key of dot. It's going to realize that it doesn't have this key of dot, because if you notice inside of our table, all we're storing is this. We don't have a key called dot. So the next course of action that the interpreter needs to do is it needs to figure out if our object has a metatable attached to it. Thankfully, it does. Now, the next course of action that the interpreter needs to do is it needs to check if it has an __index meta method, because that is the meta method used when we try to index a table with a value that does not exist. In this case, that is our dot function. So because we have defined our index meta method right here, it's going to realize, hey, great, we have an __index meta method. Let's go to the value attached to it. Now this could be a function, but the fastest way to do it is just to simply attach another table here. So then what the interpreter is going to do is it's going to hop into that table stored in our __index meta method, and it's going to check in this table if it has our missing key. And what do you bet? Our meta table does have this dot key inside of it. So the interpreter goes, great, let's go ahead and pass these original values here to this function and let the function do the rest of the work. So that's exactly what happened. If I went and removed this line and I were to run the game, we're obviously going to get into that error because there is no __index meta method in our table. So it wasn't able to find this method or this key of dot. But as soon as we add that line back and we run the game, Now the interpreter finds it and it executes the function and we get our value. Let's go ahead and keep messing with our Vector2 objects here. Let's create another function for getting a unit vector. So let's call this function something like get unit vector. And this is really easy to do. We can just return. And what we need to do is we need to divide all of the values in our object, in this case our x and our y coordinate. We need to divide those values by the length of the vector. So we'll have to create another function to get the length of the vector. So we could call this something like get length. Now, if you're not too familiar with math, you might not know how to get the length of a vector, but I'll just show you how to do it real quick. What we need to do is we need to return, and what we need to do is get the x value, raise that to the power of 2, and add the y value, and also raise that to the power of 2, and then we need to get the square root of that, and this will give us the length of our vector. And then what we can go ahead and do is we can divide our object by this length. So we could do self get length. Isn't that cool? We can just refer to our object and call the function on it, and it's going to return to us the length of the vector. Now, another issue you're going to notice is that this is bad right here. And this is bad because we have not defined a meta method for division. By default, the interpreter is not going to have any idea how to divide a table by a number. So we need to define it ourselves. So let's go ahead and create another new meta method inside of our meta table. And this is going to be for division. So this one's called __ div, short for division. And we'll set it equal to a function. And we should get past our first value, which should be our vector. So we'll just call this value 1. And then we should get our second value, which should be our number. We'll call this value 2. Now what we can go ahead and do is refer to the x coordinate inside of our vector object and simply divide it by the second value. So we'll do divide equal, and it's going to be equal to the value or our second value. And then we'll do the exact same thing for the y component and just set that equal to itself divided by this value. And then we need to make sure we return a value back out of our meta method, and we'll just return v1 back. Now this is a bad practice. I'm going to show you why in a moment. But let's go ahead and get rid of this. And then let's go ahead and create a variable. We'll call this our unit vector. And this will be equal to our vector1 object, or our vector object 1. And we're going to call our get unit vector function. And then let's go ahead and print our unit vector into the console. Let's run the game. And there we go. Here is our unit vector. As you can see, it did the proper calculation. So now our vector has a length or a magnitude of 1. Now the reason why this is a bad practice is because look what happens when I print my original vector object. We'll have two different variables here. And let me run the game. And what you're going to notice is that both of these are storing the exact same value. Our original object as well had the values inside of it manipulated. And what's actually happening here is that this unit vector is simply storing a reference to the table that's already stored in vector object 1. And that's because we're directly manipulating the values inside of our vector and we're just returning it. This is bad. What we should expect is we should get a completely brand new vector returned from this function. That way, the original vector that we called this function on doesn't get affected. This function call right here shouldn't affect our original object. Instead, we should get a brand new vector that's completely different from our original object. So the way to do that, let me go ahead and move this down below our constructor so we can actually use this function. What we need to do is we need to return a new vector too. So we'll use our constructor and pass a new x and a y value. Well, thankfully, we know what that x and y value is going to be. It's going to be equal to the x value in our original vector divided by the second value. And then for the y value, it's going to be the y component divided by the second value. And now what we have is we're going to have a new vector2 object returned instead of the original vector object right here being manipulated. This is known as something called Const correctness in other programming languages like C++. It's very important to maintain Const correctness, which basically means this value is constant. It's immutable. Do not manipulate it. We simply need to return a new object. Don't mess with the original one. So now what's going to happen is if we print these two objects out, we should get two different sets of values. So let's take a look. Oh, beautiful. Here we have our original vector with a component of 1 on the x-axis and a component of 2 on the y-axis. And then our other object is a unit vector that has a magnitude of 1. Now we can utilize our dot function to calculate a dot product. So let's go ahead and get our second vector object back. So vec2.new, we'll make this one -1 and -1. And then we'll get our second unit vector. That's going to be equal to vector object number 2, get unit vector. And then we can refer to our first unit vector, call the dot function, and pass our second unit vector. And this should print the proper dot product. So now let's go ahead and run the game. And there we go. We get a dot product of -0.94, which is basically almost opposite. Now, if I make both of these vectors the exact same, if I make this one 1 and 1, and I make this one also 1 and 1, our dot product should be 1 because both of these vectors are facing in the exact same direction. So if we run the game this time and we take a look, yeah, basically we got 1 if you round it up. It's 0.99999, it's basically 1. And then if I were to make the other vector in the complete opposite direction, we should get a value of -1. So let's go ahead and take a look. There we go, -0.09999, that's basically -1. And just like that, we have created our own custom Vector2 class. Now, of course, it's missing all of the other important functions like calculating the cross product and stuff like that. And we need to define all of the other meta methods for like multiplying, adding, that kind of stuff. But you should now have a pretty good idea with how object-oriented programming works. We have a table that acts as our class that stores a constructor. And this constructor creates a new table, attaches a metatable to it that contains functions that we can call directly upon our table or our object. And because we call those functions directly on our object, the object itself is automatically passed to those functions as the hidden parameter called self. And then we can do whatever manipulation we want to the object, and this allows us to build really complex things in our game. And of course, we don't want to forget our very important and our very magical __ index meta method here. It's extremely important to have. You actually need to have it if you want to mimic object-oriented programming using tables and metatables, because if you try to call functions directly on your table without this __ index meta method, it's not going to know where those functions are stored because you need this meta method to tell the interpreter, hey, the functions are inside of here, grab them from here. So that's all there is with object-oriented programming. I hope you enjoyed. Thank you for watching, and I'll see you next time.